Alright, up next, examples of absolute convergence, ratio, and root tests. Here we go. So the definition of absolute convergence, we say a series is absolutely convergent if the series of absolute values of the given terms is convergent. So if we can take the absolute value term by term, then that corresponding series is convergent, then the given series is said to be absolutely convergent. On the other hand, another definition, if the series of absolute values, a sub n diverges, whereas that without the absolute values converges, then the given series is said to be conditionally convergent. All right. So conditionally convergent series are kind of a pain. There's a theorem that says absolute convergence implies convergence. All right. And so here's some examples. All right. Sum n equals 1 to infinity minus 1 to the n plus 1, of course, is the alternating harmonic series we talked about in the last video. As we know, that meets the conditions for the alternating series test. So this is a convergent series, right? On the other hand, the p equals 1 series, which is the absolute value of this term by term, diverges by the p equals 1 series test. It follows then that this is a conditionally convergent series. All right. Another conditionally convergent, well, actually this next one's just absolutely convergent. The alternating p equals to 1/2 series here. So here we have a sub n is that. The absolute value is 1 over n squared. So the absolute value of the given series brings us to the p equals 2 series, which converges. Therefore, the sum minus 1 to the n plus 1 over n squared is an absolutely convergent series, because the corresponding absolute value series is convergent. All right. So I'm just illustrating the terms so far. All right. Here's one where we actually put this idea into play. So here it is. If we're looking at cosine n over n squared, we can notice that the absolute value of this series, right, is bounded above by 1 over n squared, term by term, right? So the absolute value of cosine is stuck between minus 1 and 1, so the absolute value of cosine is at most 1. So we have this inequality, and as such, we can do direct comparison of the absolute value of this series to the 1 over n squared series, right? So this converges by direct comparison to the p equals 2 series, and so it follows that the sum cosine n over n squared is absolutely convergent. All right. This is important because otherwise we don't really have it's difficult to see how you'd analyze cosine n over n squared with previous technology. It's not a series of positive terms because cosine n is alternately positive and negative, right? So we can't use limit comparison, we can't use direct comparison directly to this. This idea that we've shown you in example 3 is important if we don't have this notion of absolute convergence and using that in conjunction with other things. We're kind of up a creek for this example. Anyway, since we've shown it's absolutely convergent, the theorem tells us then that absolute convergence implies convergence, hence that's a convergent series. Ratio test. Well, here's the ratio test. If we have a series with with non-zero terms rather, and we let L be the limit of the absolute value of a sub n plus 1 over a sub n, all right? Then, if L is less than 1, this is an absolutely convergent series. If L happens to be positive or infinity, then the given series diverges. And if L equals 1, then we just can't say anything. There's no conclusion given here. If L equals 1, this test is inconclusive. As a math major, this option 3 is kind of offensive. We don't usually write this in math theorems. We're not like, it's very unusual to have a math theorem where you write the theorem says blah and blah, and oh, by the way, it doesn't say blah, and it doesn't say blah, and it doesn't say, here's all the other things that the test doesn't say. Like, it's just understood. So it's weird to me that we write L equals 1, no conclusions given here. But anyway, it's the custom, so there it is. I mean, I suppose it's good pedagogy, but there you go. So sum n equals 0 to infinity of 3 to the n over n factorial. Our nth term is 3 to the n over n factorial. If we take the quotient of a to the n plus 1 over a sub n, then we've got 3 to the n plus 1 over n plus 1 factorial. Dividing by an is like multiplying by its reciprocal, right? So the reciprocal of an is n factorial over 3 to the n. And then you do some algebra. 3 to the n plus 1 is 3 times 3 to the n. N factorial is n plus 1 times n factorial. And so my 3 to the n's, they be canceling. My n factorials be canceling. Yeah, 3 over n plus 1. Now, as n goes to infinity, that goes to 0, which of course is less than 1, right? Thus, S converges absolutely by the ratio test. Very nice. Very nice. Oftentimes, the ratio test is a good option. When we get into the next part of the course about power series, ratio test is the main event for most examples, or the geometric series. But anyway, I digress. So here's one that's always a little bit vexing to students: n to the n over n factorial. So our nth term is this. I put a minus 1 to the n in front just to make it fun. Of course, the absolute value kills the minus 1 to the n. Natural enemy of plus minus is the absolute value function. So we get n to the n over n factorial for the absolute value of a sub n. And if we look at the quotient of a n plus 1 over a to the n, we get this over that, that over that, times that over that. This is my reciprocal of a sub n, absolute value of a sub n rather. This is the a sub n plus 1. And then again, some algebra steps. We can drop the absolute value because everything here is positive. And what am I doing? N factorial. Oh, I converted my n plus 1 factorial into n plus 1 times n factorial, right? And then, what is my next move here? I'm like, oh, the n factorials cancel. Put my n to the n over here. Oh, check this out, n plus 1 over dividing into n plus 1 to the n plus 1. So that just leaves me n plus 1 to the n, right? And the n factorials cancel, and we're left with n plus 1 over n to the n, which is familiar. If we rewrite that just a little bit, right? That's 1 over 1 plus 1, 1 over 1 plus, oh, good grief, I can't talk, 1 plus 1 over n to the n, which I recall limits to e, but here's why. So convert this 1 to the infinity to exponential of n like that. So this is the useful trick to understand the limit of an indeterminate power, and this indeterminate power is 1 to the infinity. So I do that, pull the n out from laws of exponents, and then I bring 1 over n downstairs to 1 over n. Hopefully I've actually, this time I think I applied L'Hopital's rule correctly. As n goes to infinity, this goes to the natural log of 1, which is 0. And as n goes to infinity, that goes to 0. So we're 0 over 0. All right, L'Hopital's rule. And so I differentiate that, and get minus 1 over n squared, factor in both by the chain rule upstairs and by just direct differentiation of the denominator downstairs. And so those cancel. You're left with 1 over 1 plus 1 over n. And as n goes to infinity, of course, that goes to 0. We get e to the 1 over 1 plus 0, which is just e to the 1. So there you have it. So in summary, we have shown that the limit of the quotient of an plus 1 over an for the given series is equal to e, which is greater than 1. Therefore, the sum n equals 1 to infinity of minus 1 to the n times n to the n over n factorial diverges by the ratio test. All right. Now, if you're rusty on this kind of limit, specifically how it happens, how to deal with this kind of limit, you might want to look back in your textbook where limits of this type of indeterminate form is covered. It should be back close to where L'Hopital's rule was introduced. So. All right. Root test. What is the root test? The root test is the limit is a convergence test which involves the root. Okay, great. Thanks for that. But here it is. If we have a series, some a sub n, and we define L to be the limit as n goes to infinity of the nth root of the absolute value of a sub n, then if L is less than 1, the series is absolutely convergent. If L is greater than 1 or L is equal to infinity, it diverges. And if L equals to 1, then the root test says nothing. It seems like the root test and the ratio test are kind of on the same page, right? But what they're based on is a little bit different, right? So there are certain examples which are just, tailor-made for the root test. All right. So here's one. If we have inverse tangent of n over 2 to the nth power, then in this case, inverse tangent of a positive number is positive, by the way, guys. So the a sub n is this to the n, and so what my point was that the absolute value of a sub n is just a sub n. Anyway, we take the nth root of inverse tangent of n over 2 to the n, and those cancel, right? This, the laws of exponents just leaves us inverse tangent n over 2. So the limit as n goes to infinity of the nth root of the absolute value of the a sub n is just this, which limits to pi over 4, which is less than 1. Voila, this is a convergent series by the ratio test. In fact, it converges absolutely by the ratio test, root test rather. I said ratio, listen to me, idiot. Root test. This is another one that the root test is good for. Pretty much if you see something to the n power, maybe the root test is a good choice. So absolute value of a n, 1 over log n to the n. That's the absolute value of a n. And so the nth root is just 1 over log n. So limit as n goes to infinity is 0, which of course less is 1. Therefore this series converges absolutely by the root test. So there you go, a couple of examples. So next up, I'll try to draw things together and we'll look at some series, the question of whether they converge or diverge. And so the next video we're going to have all of the options on the table. Basically we'll be looking at p-series, geometric series, comparison test, limit comparison, direct or limit comparison, the alternating series idea, the absolute convergence idea, the ratio, and the root test all together at once, acting together on series. So these things all work together. So that's up next. Thanks, guys.